So we are in the second part of session 15 of the course of mathematical signal processing. We had a question in the chat right now about the use of the word algebra. And just to recall it, in this original script, you have the details about Banach algebras, Banach modules. I tried to avoid the terminology or the formal discussion a little bit, but maybe I should mention it here. A Banach space or a norm space which has a kind of multiplication. And multiplication means something behaving like ordinary multiplication of complex or real numbers, which is compatible, of course, with the linear structure. So with addition, you have distribution law or so. And it's an algebra if you have, in addition to scalar product and addition, internal multiplication. Now, we have all the time such algebras already. I mean, even if you take the complex numbers, they form the prototype of a complex Banach algebra with ordinary multiplication. You can multiply any element, so it's not necessary that you can invert multiplication in the general algebra, of course. The zero element is never invertible. You can take ordinary functions. You can take matrices which are operators from Rn to Rn. You can compose them and you have the standard rules. That's a typical example of a non-commutative algebra. We have seen that we have convolution either on the bounded measures or on the L1 space using a composition of systems or integral convolution definition or so. We have seen that there are algebra homomorphisms, which are linear mappings, which in addition respect the multiplicative properties of which turn the multiplication in L1 into multiplication in the target space, which is C0, which is subnorm, which is a norm compatible with pointwise multiplication and so on. So it's this preservation of structure and allowing us to go back and forth that is extremely important. Now, I spent some time during the weekend to also write down some thoughts that you cannot digest so quickly, but I would like to tell you, you should take a look at this text over and over again to get an idea between my approach to Fourier analysis and the approach that you get from abstract harmonic analysis. As I emphasize from time to time, I was educated in abstract harmonic analysis, and that's very much in the spirit of a book in engineering, which is called Unified Signal Processing by Gianfranco Chiarola, which was published in 2011 or so. He says, well, you know, there is a good perspective found in mathematics, but I would say it's the Book of Loomis. There's a typo here. And Rudin in the 50s and 60s, when slowly it emerged that after the Fourier transform on the real line on RD, you could do it on periodic numbers. The real setting is to do Fourier analysis on locally compact abelian groups. So this is kind of the text that I would like to quickly summarize in a few verbal expressions. Abstract harmonic analysis is interested in doing, in a unified way, Fourier analysis over general locally compact abelian groups. So while we will discuss groups also more in detail, hopefully later on, but we have seen Rn or Rd as a group. We have seen the cyclic group whenever we do MATLAB experiments. We can do a product of cyclic groups when you give me a pixel image and I apply a Fourier transform. I'm essentially decomposing it into discrete pure frequencies. And so all the time we have a translation, which is a translation on the group. So you would translate the pixel images by moving it 5 pixels to the right and 3 pixels down, but it's cyclic translation. If you have a continuous function, you would move it around in this way. And you have to ask what pure frequencies are. We will see these are the plane waves, if you take real and imaginary part or so. But in the abstract setting, you always find there is an invariant integral taking the role of the Riemann integral. There is something which I call C0. You get something which are the pure frequencies which allow to define on L1 with respect to the Haar measure some Fourier transform. But this is now living on the dual group. The dual group is not always the same as the original one. In Euclidean setting, we have this specific situation. The time and frequency variable are equal in terms of both are non-periodic and continuous. In the abstract setting, you'll find that if the group is compact, which is the classical setting of periodic functions, we are thinking these are functions on the torus, then the dual group is discrete, which means we have discrete Fourier transforms, discrete frequencies. And that's how classical Fourier analysis is working. The same thing works for two-dimensional and d-dimensional torus. So if you take images, you think you're extending them periodically and you're expanding them into plane waves, which are in a discrete setting once you have this two-dimensional torus. You can also think of the cyclic group of order n or products of such groups, and then you have the discrete Fourier transform doing exactly this kind of Fourier transform. Now this is all quite good or so, but it's like a vocabulary book. Whenever you know something on one group, specifically discrete setting, you try to understand what could be expected on another group by analogy. We will see, hopefully, and I will try to do this here in this course, that in reality you are interested to use your FFT algorithm, which you have implemented in MATLAB in a very nice and efficient way, in order to compute the continuous Fourier transform, to look where maybe the Fourier transform has peaks and so on, or you have measured data. I'm giving you an audio signal. We are computing a discrete picture, which is taken as a copy of, like a pixel version of the continuous integral transform or so. But is it justified? And the answer will be yes. If you have a nice function, and here we will use S0 as the nice function space, then everything is fine. You can compute a good approximation to your Fourier transform, which exists in S0, by taking the FFT values of samples, interpolate them in a decent way using a poo-poo, and then you're back and you have a good approximation. If you're not satisfied, make it finer and finer and take a longer and larger FFT or 2D and so on. So I think that's the extra aspect that you cannot describe if you do abstract harmonic analysis, because there you would have to choose which group you have. Also, the experience very early on was when you say you have a periodic function, then you have to distinguish whether you know what the period is of the function or whether you don't know it. Now, this looks like a strange statement, but if somebody is giving you a superposition of a few periodic functions which have incompatible periods, so a mathematician would say, I am holding an almost periodic function in my hands. I don't get everything, I get a piece of it. Well, how should I normalize it? There is no common period. So one should say, the classical theory says, if you have a periodic function, and if you know what the period is, then you can dilate it such that the period is becoming either 1, which I think is good, then you have the 2 pi in the exponent of your exponential function, and you're counting the frequencies in the unit interval, or you're taking 2 pi as a normalization, then your description with cosine and sine is a little bit more elegant, but all the formulas later on are more cumbersome. Okay, so what we are doing now is we are doing Euclidean generalized Fourier transform or extended Fourier transform, and I would like to recall a few facts so that we have a better way to work with it. So already the definition is quite simple. You're defining the Fourier transform of what I call the mild distribution in the standard way by applying sigma to f hat. Because the Fourier transform is an isomorphism of S0 into itself, an automorphism, we can show that this is giving you another well-defined, uniquely determined mild distribution, which we call sigma hat. And of course, if sigma is a bounded measure, this sigma hat is a bounded continuous function representing a mild distribution. So everything is compatible because of the density of S0 inside either C0 or the Wien algebra or so. So we would have kind of formally many different definitions if we would choose different spaces of test functions. But because of the richness of these spaces, we always have this lemma 33 of today's course in the first part, and therefore we have a fine definition which is flexible. Now, if we choose a norm, which we have a norm which is isometric, then, and this is the continuous norm, and that's why I was mentioning the continuous norm in between, then also the Fourier transform, the extended Fourier transform is isometric on S0 prime, so it has the same norm. And as we will see, it also preserves weak star convergence, but that's the next thing. Now, why is this in bijection? So is the extended, maybe if you extend a mapping which is injective to a larger space, you may lose the injectivity. So is it okay here, or is there a problem? And the answer is very simple. We can describe directly the inverse extended Fourier transform by saying, well, what you have to do is to apply the distribution to the inverse element of this here. And because of the symmetry that we have gained from the inversion theorem, this is really the inverse mapping, and therefore this is okay. Also, of course, once you have this here, you can also see it must be injective because if two elements are equal, are different, the difference has norm, positive norm, and that's also going from the time side to the frequency side. But the blue formula 242 at the moment is giving you an explicit way of coming back. I recall what the consistency principle is. It says if you're giving me a function, there's a typo, g in L1, then the mild distribution induced from the function g means, of course, integrate your test function f against g of x, not h of x. That will be controllable. Well, of course, you have to estimate the absolute value of the integral here. You can pull in always this into the integral. Well, that's now either Lebesgue integration, or you do it for dense subspace and then you extend the estimate to the limits. But in any way you control the output by the L1 norm. So actually you're having a linear functional on C0, but C0 is containing S0 as a dense subspace, so you get this estimate. Now, if you're in L1, you could take the pointwise integral transform and you can turn that into a distribution, or you can take the function as a distribution and then you take the Fourier transform. And of course, we have to, well, it's clear from the fundamental relationship that this is no problem. So it's like taking two rational numbers, either you can convert them into a decimal expression and then multiply them as real numbers, or you multiply them in the rational and then you go back. So you can switch from ordinary functions whenever they are well defined to more general functions. Now, with this tool, we're having a kind of a one-line proof that now also the inverse Fourier transform, we have seen that Dirac measures are put into characters with a minus. So I'm talking now not about the inverse Fourier transform, but the forward Fourier transform of a character. And what does it mean? It means you have to apply the character, which is a bounded function, to the Fourier transform of a head. This is integrable, so you really can just write it as the Fourier transform of this. Now, this, of course, should be, there's a stupid thing that it's not f hat, but should be y dy. And that is by the Fourier inversion theorem exactly the value of f at s, because we are inside the domain of reconstruction, which is the Dirac delta at s applied to f. So the abstract object, the forward extended Fourier transform of a character, is well defined in a naive way, a simple way, and it's giving you a delta. In the same way, of course, we have seen that the inverse Fourier transform will be, you have to take this and then you have to flip it, but the flip of a delta S is a minus S. So the inverse Fourier transform of a character is delta at minus S, or as we have seen, if you take the forward Fourier transform of delta of S is chi of minus S. So it's just the forward Fourier transform of chi of minus S is of course the delta of S. So everything is fine. Now I recall what I have already explained earlier. If you specialize to constant one, and usually you don't write this, then you get that this integral, and you should write now integration over all the frequencies, dt is the Dirac delta or so. Now in the discrete setting of MATLAB, in the finite setting, you could say, well, instead of an integral, I get a sum. So you should just add the sum of the Fourier norm, of the Fourier matrix, and you should get the unit vector at position number 1, which is the one at omega 0, because we are going through the unit roots of order n in the clockwise sense. So the point that I learned from studying many engineering books and papers is that whenever I see such an integral as a mathematician nowadays, I should say, oh, this is a symbolic representation of the Fourier transform or the inverse Fourier transform of constant one, and of course this is delta. I wouldn't like to write it as a t, so my interpretation of this is exactly, there is an extended Fourier transform which is perfectly well defined, and it's giving you the delta. It's not a function of t. I mean, of course, the inverse Fourier transform is going from frequency domain back to time domain. That's okay. That's what the variable names s and t are indicating. And then you say, as a function of s, you integrate and you get the Dirac. Well, this is going back to the time domain, but there it's a distribution. And whenever you work with it, it's fine. Okay, so we can use this also to see how the discrete Fourier transform for discrete non-periodic signals can be obtained in this setting. So we'll see how it is embedded and how discrete convolution is in the picture. Actually, we get for free discrete multidimensional convolution, but let me first do the simple case. So we have now a very nice perfect situation which says pure frequencies correspond to Diracs and Diracs correspond to pure frequencies. You can go both ways because the forward and the inverse Fourier transform are having very similar properties. You have to just take care of the sign. So if somebody is giving you a finite sum of pure frequencies, and they don't even have to sit on a lattice, so they can be incompatible. And so it's a finite linear combination. F just stands for a finite sum. Maybe I should say the index K should run through a finite set, and you have certain coefficients. That is giving you a function which is, of course, a linear combination of bounded continuous functions. So this is an element of CB. Now, as an element of CB, it is a Fourier transform, but we know how to do this. We get a discrete Dirac. So we see that this extended Fourier transform is clearly defining that trigonometric polynomials, that's the name of such functions, are going to finite discrete measures, or in the other direction, the Fourier transform of finite discrete measures are these trigonometric polynomials. Now, there are different ways of forming limits. For example, you can say I'm taking infinite sums with coefficients which are absolutely summable, which is maybe the next step. So we take those infinite sums where you can, the first thing may be just take infinite sums without taking care of what the SKs are, what the frequencies are. Then you would still have that this is the Fourier transform of a bounded measure, because if you have a bounded sequence of coefficients, then whatever the SKs are, you get a bounded measure. And you recall maybe that if you have SK pairwise different, then any such expression in its canonical representation has the MB norm, which is you apply it to the C0 function, and so it's exactly the sum of the absolute values of the CK, even if this is a complex valued function. So that's one limit. The other thing is you can take the uniform limits of such trigonometric polynomials with free coefficients. That would bring us into the theory of almost periodic functions. These are functions which are not periodic anymore if the SK are not sitting on the lattice, but they're almost periodic. It's like the sun and the moon and so on. So if you look, the periodicity of the moon is not an exact periodicity, but almost periodicity arose from the observation that if you compare the situation, you have a very similar situation over a very long interval sometime in the future. So if segments of the given situation repeat themselves, not exactly, but approximately after a sufficiently long waiting period, that's why the notion of almost periodicity came up. But it's kind of a closure in CB with the supremum of these guys. And then, of course, you expect that they have Fourier transform in the setting of S0 prime, which is true, and you can pull them out by focusing on the frequencies which are inside the signal. I'm not sure, but I think we will not have time enough in the course to discuss this. But this would be the entry point for the modern theory, distribution theoretical view on the theory of almost periodic functions. Now, if you are doing the same thing with points which are on a lattice, so in the one-dimensional case, you would have multiples of integers, or just take the integers as a first example. And if you take summable coefficients, then the MB norm and the coefficient norm are the same. And we are asking now, what happens if you're convolving two such discrete measures? That's kind of the entry point into discrete convolution or so. Well, if you take infinite sums, you can approximate them by finite sums. So let's try to understand what happens with finite sums. Well, we will get a bunch of expressions from delta lambda convolved with delta lambda prime. If you change the indexes, so maybe I put lambda prime and lambda double prime, but we don't get arbitrary deltas. It will be always a sum of lambda prime plus lambda double prime from the lattice. So we will get certain points, and if it's a lattice, it just means that all those sums are part of the original lattice. Now, if you're resorting everything according to the lambda that has been achieved, you're getting these sums. So it's exactly the Cauchy product. The first expression is easily telling you that you're getting a symmetric object. The other one is more the programming that you're saying, well, how can I get, in the integer case, a contribution to a lattice point n? That's the coefficient at lattice point n. That's n1, n2, n3, up to nd. And you're saying, well, you're summing up all these coefficients which add up, where the indices add up to the given n. So you can say, well, I'm doing systematically which ones from the first lattice paired with the other give n, and of course it has to be the complementary n minus k. Now, we have seen such a scalar product already, of two interpretations of the convolution. One is to say, well, we are living now on a discrete, locally compact group, so we are having a convolution already defined. We have to take the sequence, C1, for example, we flip it, so replacing indices by in negative indices, and then we shift, then we take a scalar product. So this would be one way to describe the convolution. The other way would be, of course, to relate it to the multiplication of polynomials, and I think that's what I will do later on. Yeah, okay, so I'm sorry. I will come back to this, but I think you can see already here, if you look back for the convolution product here, it's the convolution product of discrete measures. And we will also hopefully see how to relate it to discrete probability measures. So if you want to see how, I don't know, something is heat is distributing on a discrete lattice, or how infections are spreading out. That's a modern example, or how plants their seeds are getting moving around by the thing. Then you can see how it involves, and you have maybe two-dimensional Gaussian shape after a certain while by iterated convolution with a certain probability density. Okay, so I will try to go now to the continuous setting, no, to the discrete setting, where we take the standard lattice, which is just a dilated lattice of a d-dimensional lattice, and after all, I will take the one-dimensional situation. So we have seen that bounded continuous functions can be viewed as mild distributions. So that's just a repetition of what we have before. And that, of course, the generalized Fourier transform that we have defined for mild distribution is the same, it is giving us the same as the one that we have already for bounded measures. The point is that we will be able to extend it now. Maybe the claim was that Fourier was starting from periodic functions, and he was making the claim that every periodic function can be expanded into a Fourier series. Looking from a present viewpoint, this is a courageous statement, but they had no idea what really a function is, what it means to compute Fourier coefficients by integrals. That was the work of Riemann and then Lebesgue, and what representing means, meaning how to get back from a Fourier series to the original function. This was a miracle for the whole 19th century, until it was realized that there is a nice way to interpret it, and that was the beginning of functional analysis. And so I would like to recall you what is the classical approach to Fourier series expansion. So we should not look at only Fourier coefficients and how they allow to do the inversion theorem. Even if you have L1 functions, you have a nice forward Fourier transform, you get Fourier coefficients, but you would like to say, no, the pure frequencies on the torus or on the unit interval or on the interval from 0 to 2 pi, they are forming an orthonormal system. And the orthonormality is taken with respect to the scalar product, which is written here. So in a d-dimensional setting, you're saying, I'm taking all the values of one element, one vector, one function against all the other values, and they're collected by an integral. This is defining a scalar product with all the same properties of this here. And the great thing of Lebesgue integration theory and early functional analysis was to recognize is that here you can work with an orthonormal system, very much like the x, y, z coordinates in R3. You can describe a vector of its length by taking the sum of the squares of the components. And if you do this in a continuous way, you find yourself in the following situation. I'm just summarizing the classical theory. The pure frequencies fitting to the periodicity are those of the form k, so exponential function with integer exponent. It can be multidimensional. And this representation is understood in the sense that partial sums are convergent because you are finding that the L2 norm equals the L2 norm here. This is the continuous L2 norm over the cube, or on the d-dimensional torus. This is the Plancherel theorem in a concrete form. The Fourier transform square integrable function on the torus are nicely integrable. That's a very big advantage of the compact situation. Therefore, these Fourier coefficients are nicely, they exist in the Lebesgue sense, and they are scalar products of f with the k. So this is kind of giving a nice interpretation of the situation. You even have, the polarized version, so scalar products at the coefficient level are equal to scalar products at this level. And so the question is, how can we extend or embed this theory into our setting? I spent some time on playing around to do it. So maybe you find the next segment a little bit cumbersome or so, but maybe at the end of the course you're appreciating that this theory of mild distribution, or the approach that I was using, a pedestrian approach, is still allowed to do this. So the first thing is, if we want to understand this classical theory in the framework of mild distributions, we would start with the dense subspace. And of course, we choose the absolutely summable sequences. So L1 is the sequence of coefficients which have a finite sum of absolute values. And they are inside the square summable ones. If you take now these coefficients, we have seen you get bounded measures, you get Fourier transforms, and we call these Fourier transforms elements of the absolutely convergent Fourier series. Now, why can I put A of t? Because each of the characters with integer frequencies, let me reduce everything to the lattice now, integer lattice, set d, they will, or even set integers one-dimensional, they are periodic functions. And here in this statement, you have identification of truly periodic functions on the real line. So that's kind of the periodic pattern on the wall with the function, which is the waltz, which was doing that painting on the wall. I will also show you with the stem sil command in MATLAB how this wrapping up on the torus is happening, but we will use this. So instead of starting on the torus and doing integration on the torus, I will say, no, we have periodic functions and they are expected to correspond to coefficients. So let us start with the coefficients. So the way how I will do it is, in order to achieve the analogy or the interpretation of the classical theory in our framework, is to say, I try to do an interpolation of the sequence by producing a nice function, actually a band-limited function, by interpolating with the sinc function. Recall the sinc function is the Fourier transform of the boxcar function, of the symmetric version of the boxcar function, and it has the value 1 at 0 and 0 elsewhere. So if I take at every position k the coefficients, I will get a function which at the point k has the value c1 of k, and you move around and you get no contributions at any of the other points. So we can say this function is a well-defined function. It's an absolutely convergent sum of a bounded function. I mean, they all have the same norm. In the supernorm, it's norm 1. So this is nicely convergent, a bounded continuous function. But we can also interpret it as a convolution of the sinc function with a bounded measure. Well, this is a convolution of something which is a bounded measure with formally with an L2 function, but you could say I'm doing the same thing on the Fourier transform side and then take Plancherel transform. So this is a well-defined continuous function and it's periodic, and that's why I call it a function on the torus. The supernorm estimate is also quite easy. It's by the bounded norm of this here, which is just the L1 norm of the coefficients, and this is just some bounded function, and this is the embedding constant. So we have something harmless. Now, Plancherel is extremely helpful because it allows us to argue that convolution in any reasonable setting, if it's defined on both sides more or less, goes to pointwise multiplication. Sinc function goes to the boxcar function, and h1 of hat is just this infinite sum. So we get a really periodic function, but it is then multiplied with the boxcar function. So this particular function f has a Fourier transform, which is a pointwise product. So when we want to see how we can get the scalar product of coefficients interpreted as an integral over this unit interval, symmetrically around 0, we just have to say, well, now we would like to multiply this localized version of h1 with the function h2, which of course is the periodic function arising from the second set of coefficients, also in L1. And so the question is, how can we get this integral or so? Okay, we just have to define a measure. So I'm going the opposite direction. the measure is now the discrete measure, and its Fourier transform. Its Fourier transform is exactly our function h2. Now, what I want to do is to show that in our framework with the fundamental relationship, we can get the left-hand side, which is the scalar product in the spirit of the Hilbert space L2 in the discrete setting by just applying this particular discrete measure to the function f. So once more, we have three ingredients. I could call it maybe nu1, which was the original function giving h1, so it's having this Fourier transform. We have the second set of coefficients, which gives a nu2, which I call nu here, which gives a periodic function. But then in order to get something which is of the right shape, we convolve the first bounded measure with the sinc function in order to get our function f. Because on the other side, we need only h1, h2, but localized. So we have to multiply the red guy now with the h2. Again, on the left-hand side of the fundamental relationship, we can say, well, we have a measure applied to a function. Actually, that function is a Fourier transform, so we can apply it, but let's just do it. So it's a linear combination of Dirac measures applied to f. Now, Dirac k at f is just f at k, but this was made to be exactly ck at 1. So this is just the interpolatory property of the sinc function, which says, oh, nu of f is just a scalar product at the coefficient level. Now, if we want to do this and justify this limit relationship or so, either we have to do it that these kind of functions and these kind of measures are okay. So, but the f is not exactly a measure, so we have to be a little bit careful. I don't go through the details, but I will say, well, I try to approximate the nu by Fourier transforms. So I would like to say we take a triangular function which is using these coefficients, actually the conjugate of the coefficients, because I also have conjugation in my measure nu. I'm doing the same trick as we did in the inversion theorem. The main point is just look quickly. We have the we have the triangular function here. This is an element of S0. Dilating it with a fixed rho is giving you a broad triangular function. This is in S0. Multiplying it is in S0. These elements for fixed rho all have the same norm. Modulation doesn't change the norm. Therefore, with L1 coefficients, we get something which is a absolutely convergent sum. So this is an element of S0. So we can apply the Fourier transform, which turns dilation into compression, modulation into shift parameter. So we have such a function, and that's again absolutely convergent or so. But now we want to know what happens with these terms. So this is sum of terms. And these terms are sinc square functions. This is an element which is in L1. If you compress it, you will get a Dirac, and the amplitude will be exactly the integral of a sinc squared. But the integral of a sinc squared is just the Fourier transform of sinc square. But it's a symmetric function, and the symmetric function, the inverse and the forward Fourier transform are the same. We know sinc squared comes from the triangular function, so the integral is exactly delta at 0, which is 1. That's why this ST rho of sinc is converging to the delta at 0. If you shift everything, it's going to the delta k. So if you glue it together, we have in the fundamental relationship something which is a nice Fourier transform of a nice object, which is approximating our nu, and this is going to this expression, which, as we have seen, is the scalar product. So here we write it here. So the justification is coming by taking the limits, whereas on the other side, we have the other side of the Fourier transform is we have h1 localized with this g rho, and this g rho are now, of course, the approximation. They are not exactly the h2, but they are h2 multiplied with a dilated Dirac. But this is going to constant 1, so you're stretching and making it flatter and flatter, so you have uniform convergence over compact sets. So eventually, over the area of interest, where this function is living, actually you are just taking the unit cube, you make that function delta in the dilated version so close that this is in the limit giving the integral. So I'm just telling you, and you don't have to study this proof in detail, that if you do the right choice in the fundamental relationship, and if you are able to justify the limit, taking the limits, you can get this relationship. So I hope I can do the at least indicate the proof of the Poisson formula in our setting of mild distribution, which is one of the key results in distribution theory, but also in order to allow to prove the Shannon sampling theorem, to understand that sampling corresponds to periodization on the Fourier transform side and vice versa, as we have seen in the MATLAB experiment already. Now there are two, or I will show you three forms of Poisson's formula. The first one I would say is the mathematically precise result, which is a result in analysis. It simply gives a remarkable identity saying that any function in S, I'm doing the one-dimensional situation, but you will get it more general in a moment. Every function in S0 has the property that the sum over the integer values of that function is absolutely convergent, and it's equal to the sum of the Fourier transform of the function. Now, this is where the choice of the 2 pi and the exponent of the Fourier transform pays off. We don't have any pi anymore, and we have no factors in front of this formula. If you look at the literature, you will either find that this is true whenever both sides are convergent, then this is not a valid mathematical statement. There are counterexamples where both sides are well-defined but are not equal. On the other hand, if you look at all the arguments that you find in the literature, I have not found any one which is more general than this one. In other words, the usual conditions that you find in the literature, like f is integrable and also the first and the second derivatives are integrable, well, this is just a sufficient condition for being in a zero. So it's really the most general result that you can have. Now, how does it relate to the Dirac comb? Well, we have seen that Dirac comb belongs to the space of mild distributions, and therefore it has a Fourier transform. And the claim is that this formula is equivalent to the claim that the Dirac comb is invariant under the Fourier transform. Now, if you look at this left expression, it simply means that the Shah distribution applied to f is the same as the same Shah distribution, now an independent variable, applied to f hat. But by definition, applying a distribution to a Fourier transform is the same as taking the Fourier transform of this to the f. And that's why the Poisson formula is really the same as this. Now, some people may say, well, we know this, I have seen this already in a course on distribution theory on template distributions. Well, that looks like the same formula, but it's much more restrictive. In that setting, you would say, this is only true for Schwartz function. This is a kind of a relatively small subspace, still dense, but small subspace of this. Here you can put even piecewise linear functions there in S0 if they're integrable, and you still have the identity. So it's a rather big reservoir that you can have here. Now, if we recall that the Dirac comb is a sum of measures, you can say, well, I apply the Fourier transform to the individual terms. Then you would say, I'm summing up over all the pure frequencies. Now, one has to justify the left-hand side in the sense of saying, well, it's true, yes, you can have convergence as a mild distribution. The limit of the partial sum are working whenever you apply it to a function. So then you're actually getting something like this. And it's the same as the sum of the deltas. So I don't like it too much, but you can reinterpret this formula in this way. But then engineers would say, oh yes, characters are the e to the 2 pi I. I'm summing over the integer lattice. And this is a symbol which can be read as the Fourier transform of the Dirac comb. And it's the same as a function of t, to indicate on which side we are, of the Dirac deltas at the integers. So this has to be interpreted as an infinite sum in the sense of distribution. This has to be interpreted, and then it's, I would say, morally equivalent to the statement Rousseau. Now, I have no time to go into the proof, but at least as a first indication how it works, we will recall that what we do is really, we can say, take the Dirac comb and convolve it with your function f in S0. And that gives a sum of delta x with f. It's justified to kind of pull in, change the order of summation with the convolution because it's continuous. But again, even that would require some argument. But the point is, you're getting shifted version of f. So we are producing a periodic function from the given function. And the main point is, our functions f are in the Wiener algebra where this makes sense in a uniform way. Therefore, also for S0, this is fine. And the key point is, why can we expand this function into periodic Fourier coefficients? And then, but I will do this next time in more precision, is the Fourier coefficients of the new periodic functions are exactly the samples of the original function. So f hat of n means you're giving me a function S0, you're taking the Fourier transform, and you're sampling it at position n. And that turns out to be exactly the Fourier coefficient of the periodic function, which is the coefficients fn, or the scalar product of f periodic against the character with frequency n. And that allows you to have a representation, and that will be reinterpreted as Poisson's formula. So I will go back to the Poisson formula, and we will evaluate the usefulness of the Poisson formula in our next unit. Therefore, I'm thanking you for your attention and closing the session now.